Hi, we are Team 16. I'm Vincent, and our project is thermal modeling and temperature control of the lunar regolith. So, to start things off, right now, exploration and colonization of the moon is a hot topic of discussion for countries around the world, especially since NASA and SpaceX have plans to establish a base on the moon within the next 5 years. However, there's an issue. The environment on the moon is very harsh. There are 14 days of daytime and 14 days of nighttime. And the temperatures can get as hot as 110 degrees Celsius and as low as negative 190 degrees Celsius. And electronic devices will fail under these extreme temperatures. However, under the lunar surface, what's called the regolith, it has been observed that there is a constant negative 20 degrees Celsius at a certain depth. And this is very promising. There's even been research already done on devices or systems that utilizes the regolith's natural heat retention properties to create a sustainable environment for devices. This, by extension, means that there can be a livable environment during the cryogenic temperatures of lunar nighttime. But the issue with previous research is they've used a homogeneous and uniform granular simulant, typically being some sort of sand or volcanic ash. But we know that from the Apollo missions, when a core was extracted from the lunar surface, the sample was observed to be stratified. There are different layers and different sizes of grains. And on top of that, we know things like thermal conductivity, specific heat, and density all vary with different depths and temperatures. So all these factors combined will make obtaining an accurate thermal model difficult. So the need we plan to address is obtaining an accurate model of the heat diffusion through a heterogeneous lunar simulant. And we plan to improve our experimentation by including all these factors that I listed before. And our approach is using deep learning. One of the beauties of deep learning is we can disregard all these factors, yet still obtain an accurate thermal model. The more sensors we have in our simulants, the more accurate our neural network can be to obtain a good model. And like I've said, there's large promise in utilizing the regolith. We've seen proposals for large systems that can store heat during the daytime, or things like a solar-powered heater that can heat the regolith for later use. This will all be useful, especially with all the astronauts on the moon in 5 years. It surely would be beneficial to have other methods to heat the environment other than purely relying on nuclear energy. There's even been TED Talks about having just a colonization of the moon underground. And there's been visuals provided too, such as that. So, this is our proposal for a vacuum chamber system. This is our cooling system. That's our vacuum pump, and this is our thermal chamber itself. And we've been fortunate enough to work with Suri and UTSA faculty Dr. Jin, who have been providing us with the most equipment that we need. And now I'll be passing things off to Tommy, who will explain the specifics of our system.
All right, thank you, Vincent. So, we've been working very closely with Southwest Research Institute on the design of our vacuum system. Currently, they are supplying the physical vacuum chamber that we will be using, along with the vacuum pump that we'll be using to reach high vacuum pressures in that vacuum chamber. Dr. Jin will also be supplying us with our DAC system that we will be using for data collection, and our group will be designing a heating system, cooling system, heating shroud, and a data collection system. Now, for the overall vacuum system, we're designing several different component feed-throughs that will allow systems inside the vacuum chamber to communicate with systems outside the vacuum chamber. Among those feed-throughs will be a liquid nitrogen pipe for our cooling system, an electronics wire feed-through for our heating system, and a thermocouple feed-through for our data collection system. We're also looking into adding ceramic standoffs to minimize the amount of contact between our heating shroud as well as radiative shielding to minimize the amount of heat loss in the system. Now, the core of the vacuum design revolves around the use of a hollow aluminum cylinder, which we will call our heating shroud. And the heating shroud's purpose is to contain lunar regolith simulant, and we'll attach our heating and cooling systems to that heating shroud to control its temperature, and thus the temperature of the regolith inside the heating shroud. Now, the core of the cooling system revolves around the use of liquid nitrogen. Liquid nitrogen will flow through a series of pipes that wrap around the heating shroud, and that pipe system will be controlled through a solenoid valve, which we can control electrically using our control system. The pipes themselves will be made of high purity aluminum because it has very efficient thermal conduction between the pipes themselves and the heating shroud. Now, the heating system works in a very similar fashion, except instead of using liquid nitrogen pipes, we'll be using a nichrome wire circuit that wraps around the heating shroud, and it will be connected to a variable power supply. We can control that variable power supply electrically to control the voltage being supplied, and thus the power dissipated by the nichrome wire and the heat dissipated to the heating shroud. We are also looking into using a UV heating lamp as another source of heat, and that will simulate solar radiation hitting the lunar surface like you'd expect during a lunar day. Now, as far as the simulant, we're planning on placing approximately 50 centimeters of lunar regolith simulant deep inside the vacuum chamber. And the simulant that we're planning on using is Nipa basaltic ash. And we chose to use this particular simulant because its thermal properties are very similar to those found during samples obtained during the Apollo missions on the lunar surface. The exact way we'll be measuring the temperature is we'll be placing a network of approximately 40 T-type thermocouples at various depths and locations inside the lunar regolith. Those thermocouples will exit the vacuum chamber through our feed-throughs and connect to a DAC chamber that we'll discuss more later on. Now, the control system itself revolves around a proportion integral derivative controller, or a PID controller. The PID controller will connect to both our heating and cooling systems and will allow us to control the temperature of the heating shroud and the simulant inside of it as well. One of the main reasons why we chose to use a PID controller is previous research has shown or has been done using PID controllers, so we will be able to verify our system's accuracy versus past systems and see how well the control system works. And now I'll be passing it off to Josh to talk about the control systems more in depth.
Thank you, Tommy. Like Vincent had mentioned, we know from coring samples of the Apollo mission that the surface itself is not uniform in nature, but is actually stratified. This is due to meteor impacts and volcanic eruptions that happened billions of years ago. These imperfections on the surface change the thermal and physical properties of the regolith. A PID controller requires rigorous calculations and properties of the material to be known in order to design a controller, such as the one Tommy was mentioning.
So in order to forget these properties and to be able to model the heterogeneous surface, we plan on using a neural network. The glory of using a neural network controller is that we don't have to know the actual system to control it. It's almost like a black box. The network will replicate this black box by a series of training, and it will recreate and act exactly like the system we want it to. The overall idea of a neural network is to be able to map out physical properties of the material without knowing the actual numerical value of the physical properties. Once we have trained the system, the controller should behave as desired. Also, we hope to be able to predict the temperature at various depths and map out the temperature of the simulant.
In order for a neural network to train properly and accurately, we must have a large number of data inputs. To fulfill this requirement, we will use 40 T-type thermocouples strategically placed all around the shroud in order to get the measurements around the simulant. Placement is important because the thermocouples will create an air gap between them, and this will distort the properties of the material, which may produce inaccurate results. We chose to use T-type thermocouples due to the accuracy at low temperatures. Since we require a large amount of data input, we must have a data acquisition device that can read all these inputs at once. For that reason, we plan on using the NI National Instruments PXI 1042. It has a high accuracy of 1/10 of a degree and has high-speed collection of data and a sampling rate. This will be provided by Dr. Jin due to its large cost. So for our tasks, it's these as follows. So we have the vacuum design. This involves the feed-throughs like Tommy had mentioned, and the different connectors, and just how we plan on implementing the exterior part of the vacuum chamber. The next step is determining what materials for the shroud we want to use. So we need something with a high connectivity, so that way it would be able to transfer all the heating and cooling from the pipes and the nichrome wire into the simulant itself. So we're stuck between copper and aluminum, but we're mostly leaning more towards aluminum due to its availability to find. The next part is to actually machine the shroud. So we need our parts cut, the pipes bent to wrap around the shroud, as well as welding to the shroud itself to allow effective thermal transfer. After that, we have assembly, which involves putting the sealant inside, putting the the thermocouples inside the simulant, and measuring the temperature around. From there, we would do PID testing to see if our system behaves just like previous research papers. Next, we will then make the simulant heterogeneous by changing the density and how much is compacted and everything. And from there, we'll use our deep learning to determine the properties of this material. So now for the constraints. Some constraints holding us back from creating a 100% simulation of the moon is mainly cost. The instruments required for this project are well over $1,000. So we're limited to using the specific instruments and materials provided by Dr. Jin and our mentor at SWRI. In order to simulate the lunar environment, we have to be able to heat and cool for 14 hours straight. So since our project is located at SWRI, we must find a way to automate the process, since we will not have access to the building itself after hours. Another a constraint we're having, is that we realized after a few meetings with our mentor at SWRI that a lot goes into vacuum design. So there must be the correct feed-throughs to allow communication inside and outside of the vacuum. Moreover, certain materials will outgas whenever it's under a ultra-high vacuum, making the process of creating a vacuum much more difficult. Lastly, finding a high-grade material is both expensive and difficult due to its low demand. We are restricted to only using what we can find as an alternative for these materials, which will hopefully work for our use. As for potential expansion, our project can be used all over the space community. Currently, there's a large interest, like Vincent had mentioned, to expand our knowledge of the lunar environment. This chamber will provide a platform to test devices in order to develop solutions using the lunar regolith, in order to heat devices, or we can also determine different ways, effective ways to drill into the extremely dense regolith. Further, since we have a neural network, we can use our mechanisms to simulate environments on other planetary bodies such as Mars. All we would have to do is retrain the neural network from data from these other planets, and we should be able to simulate a similar environment. Thank you for listening to our presentation.